Let's get started. So welcome everyone. I'm Abby Lindberg. I lead GelSight's applications engineering team. I'm here at our headquarters in Waltham, Massachusetts, right outside of Boston. And with us remotely, we have Pat Stack, our principal software engineer and resident surface texture expert. Pat has over 25 years of experience writing surface metrology software and is a former member of the ASME B46 Standard Committee on surface texture classification. So this webinar is the first in a series about surface texture and roughness. And today, Pat is going to get into what is surface texture, and then into some detail about the RA parameter. We'll follow that with a live demo and Q&A. So throughout the presentation, feel free to use the Q&A functionality at the bottom of the Zoom window to send questions over. So before I hand it over to Pat, I'll start with a little bit about GelSight. GelSight is a portable measurement system that can be used to characterize a 3D surface in a matter of seconds. The form factor lets us get into hard-to-reach locations, and the gel sensor lets us look at any material regardless of optical properties. So we like to say any material anywhere. And we mean any material anywhere. So here we can see we've got wood grain, we've got snow crystals, we've got 3D printed metal, fish scales, and other machined surfaces. Anything from matte black paint to chrome. And here's an example of a highly reflective surface. So on the top, we have a scan and profile taken with a GelSight system. And on the bottom, we have a scan and profile taken with a competitive system. So GelSight eliminates those issues caused by reflectivity and transitions between surface materials that lead to spikes or dropouts in the data that you can see on that profile at the bottom. That's typical with a lot of competitive measurement systems. So the GelSight system consists of a camera and illumination system, and then a soft gel sensor. And the soft gel sensor will be pressed against the surface that you're inspecting, and it's not going to damage the surface like a stylus might. And the pigment layer on the gel is what lets us look at these surfaces regardless of those optical properties, because we're actually looking at the surface through that red pigment layer. So with that, we're going to be able to quantify surface measurements, quantify our surfaces in seconds, with NIST traceability and a digital twin of the inspection area. So the scans that we're going to review in this series are going to be taken with the GelSight system. And with that, I will hand it over to Pat to get into what is surface roughness and surface texture.
Thanks, Abby. So since our attendees today are from so many industries and have various levels of knowledge regarding surface texture analysis, I'm going to begin with the very basic question, what is surface texture? Sometimes the surface texture is also referred to as surface finish or even surface topography, and for the most part, these terms can be used interchangeably. Surface roughness, however, is the analysis of a specific bandwidth of wavelengths within the surface texture. I will be talking more about this in a few minutes. In layman's terms, surface texture analysis is the measurement of the relative smoothness of a surface. It is calculated from the small deviations from the surface's nominal shape. The larger those deviations, the rougher the surface, and the smaller those deviations, the smoother the surface. As you can see in this image of a typical surface texture plate, it has several example textures. You can also see the surface deviations increase as you look from left to right. Looking at this surface plate, you can see that it is critical to determine the desired surface roughness of a part before the manufacturing process begins. The surface texture can influence how a manufactured component will interact with its environment. That can be the mechanical friction of one part with another, or simply the visual impact it has on you while looking at the surface. The surface texture may have a significant impact on the performance and longevity of components in many engineering applications. For example, a smoother surface texture may be optimal when designing a part that will slide along another part in order to reduce the friction between those two parts. Also, rough surfaces tend to wear faster than smoother surfaces. However, manufacturing costs can quickly skyrocket as the required roughness is reduced. So it's very important to know what level of roughness is required for the component that you are manufacturing. In some cases, it can even be desirable to have a rougher surface texture on a part. For example, the post on a bicycle seat that needs to have a high coefficient of friction so that it does not slip down easily while being adjusted. We typically measure the surface texture to predict the performance of a component, but we may also measure a surface to help control the manufacturing process itself, because the machining process leaves a signature in the surface texture. Every surface has some form of texture that is a result of the way the surface was produced. In a 2D profile or a 3D surface, you can think of this as a series of peaks and valleys. These peaks and valleys can vary dramatically in width and height. Sometimes a surface will have a uniform repeating pattern due to a cutting tool, such as a lathe, or sometimes the surface appears more random, such as after a grinding operation. If the surface has a dominant pattern of texture, lay is the term used to indicate the direction of that pattern. When I began to learn about surface texture nearly 30 years ago, I was still a working musician, so at that time it helped me to relate the concept of surface texture filtering to music. I think that this comparison may be helpful to you as well. All signals, whether they be audio signals or measured profiles, can be analyzed for their wavelength content. Every signal is composed of sine waves of various wavelengths that can be separated or even combined again to recreate the original signal. In the audio world, these sine waves are typically described by their frequency. In the surface metrology world, we tend to think of these sine waves in terms of wavelengths. Perhaps you may recall from school that the frequency is simply the reciprocal of the wavelength. In other words, high frequency signals have short wavelengths and low frequency signals have long wavelengths. In music, the kick drum and the bass guitar, my personal favorite, make up much of the low frequency content, while the lead guitar and the snare drum make up much of the mid-range frequencies. And the cymbals and the high notes on a piano might make up much of the high range frequencies. If you ever adjusted the bass and treble settings on your car or home stereo, I'm sure that you noticed that you can boost or lower the frequency content that most suits your taste. Decreasing the level of a signal is known as attenuation. I'll be talking more about that in just a minute. The analysis process in surface metrology obviously doesn't have anything to do with music and audio signals, but the concepts are quite similar. In our case, the input is not an audio signal acquired by a microphone, but the measured profile acquired by a GelSight system. This measured profile could also be acquired by a contact stylus profilometer, or an optical system, or by some other method. In surface texture analysis, we separate the wavelength spectrum into 3 elements or wavelength regions: roughness, waviness, and form. The form is the general shape of the surface or the longest wavelength information of a profile measurement. For example, if you were measuring the surface texture of a basketball, the form would be the sphere of the basketball itself. In today's webinar, I'm going to focus on the analysis of a 2D profile instead of an area or a 3D surface measurement, simply because it's easier to visualize. But keep in mind, the concepts are very similar when analyzing a surface or a profile. As I mentioned earlier, a profile can be acquired by multiple methods. In the case of a GelSight system, a 3D model of the surface is acquired, and then a 2D profile can be extracted from anywhere on that scanned surface. In fact, Abby will be demonstrating exactly how this is done in just a few minutes. So the processing of the measured profile data follows the steps in this flow chart. Obviously, the first thing we need to do is find something interesting to measure. The surface or profile is sampled and digitized. When using a profilometer or a GelSight sensor, This is done by the contact of one mechanical surface with another. This could be the spherical stylus tip of a profilometer, or in the GelSight case, it's the gel itself. The remaining steps in the flow chart are all performed in software, even though at one time, some of these steps were done using analog circuitry and chart paper. We should all be very happy that this is no longer the case. The extracted profile contains all of the wavelengths capable of being measured by the measuring instrument. I often hear people refer to this profile as the raw profile. The next step is to remove the form from the extracted profile. Keep in mind that the form is the longest wavelength information or content in the extracted profile. This is typically done by fitting a geometric primitive that matches the shape of the profile being measured. This could be a line to simply level the profile data, or a low-order polynomial curve on a curved surface, or even a circle if you're measuring a spherical component. On this slide, I'm attempting to show that a best fit line has been fit through the profile data in order to level it. The top chart shows an extracted profile with the line that has been calculated, and the bottom chart shows the leveled profile data relative to that line fit. The wavelength spectrum in the lower right corner of the slide shows that the longest wavelengths, the form, have now been attenuated or removed. The next step in the processing pipeline, as I like to call it, is to remove or attenuate the very short wavelength information below the lambda S wavelength. This wavelength is called the roughness short wavelength cutoff in the ASME standard. This wavelength is typically 2.5 microns on a contact profilometer and is used to remove noise from the measured profile, since the profilometer cannot measure these very short wavelengths due to the radius of the stylus tip. The resulting profile is called the primary profile. Using the primary profile data, we then separate the short wavelength content from the long wavelength content. The exact wavelength we choose to separate the wavelength information is known as the lambda C wavelength, or the lambda C filter cutoff. The resulting profile containing the wavelength information shorter than the lambda C wavelength is called the roughness profile. And the resulting profile containing the wavelength information longer than that lambda C wavelength is called the waviness profile. I will be discussing the RA parameter in some detail very shortly, but keep in mind that the R in RA means it is calculated from the resulting roughness profile. There are also P and W parameters that are calculated from the primary and the waviness profiles respectively. So at this point, you may be asking exactly how do we separate the wavelength information in a profile? In an ideal world, the roughness profile would contain 100% of the wavelength information below the lambda C cutoff and 0% of the wavelength above the lambda C cutoff. But we can't do this exactly, so the best option we have at the moment is to use a Gaussian filter. A Gaussian filter can be used as a high-pass or a low-pass filter where 50% of the signal is attenuated at the cutoff wavelength. Notice in this image how the transmission regions have a smooth roll-off zone around the cutoff values. The Gaussian filter is a convolution filter, which means it is applied point by point along the primary profile data. At each point along the primary profile, the filter performs a weighted average of the surrounding points based on the bell-shaped Gaussian distribution curve shown in this image. The points close in distance along the x-axis to the point being processed are weighted more heavily than points further away. In fact, points further away than half the filter cutoff have weights so small that we can safely assume the weight is 0. The overall width of this bell curve shape is equal to the filter cutoff value. Because this filter requires data to be used both before and after the point being averaged, the algorithm cannot start processing the data at the very ends of the primary profile. You can see that the roughness and waviness profiles are shorter in length than the primary profile by 1/2 the lambda c wavelength, both at the beginning and the end of the profile. The longer the lambda c cutoff value, the more data that must be discarded to compute the roughness and waviness profiles. This missing profile data at the beginning and the end of the profiles is known as the end effect of the filter. I get asked all the time, what filter cutoff should I use to measure my part? Well, unfortunately, without knowing the intended functionality of the part, this is not a straightforward answer. Ideally, the value of the lambda c wavelength should be specified on the drawing by the part designer. However, this is often not the case. There are some tables in the latest ASME B46 standard that can assist in determining this value, but being that it is dependent on the function of the component itself, there is not one correct answer, so this may be a topic for a future webinar. So now that we have our primary, roughness, and waviness profiles containing the wavelength information that we are interested in, what can we do with this? Well, sometimes it's simply looking at the profiles themselves that will give you much of the information that you need, but not always. Quite often we need to quantify or put a number to the profile data. I'm sure that you noticed the numbers located above each of the example surfaces on the plate from the beginning of the presentation. These values represent what is commonly known as the average roughness or the RA value of each surface. The lower the RA value, the smoother the surface, and obviously the higher the RA value, the rougher the surface. So by calculating the RA parameter, it helps us to get a general idea on how rough the surface is. The length along the x-axis from end to end of each of the profiles is known as the evaluation length. The RA parameter is calculated over the roughness profile's evaluation length like this. First, the mean value of all the points is computed, and the profile data is normalized so that the mean value becomes 0 on the chart displayed in this slide. This 0 reference line is also known as the mean line and is the thick horizontal line in the image. Any points located in the valleys below the mean line are inverted, and then all the points are averaged to compute the RA parameter value. In mathematical terms, this is the average distance of the roughness profile from the mean line of all the data points along the evaluation length. As I mentioned earlier, this is why RA is known as the average roughness. However, many years ago, RA was called CLA, or center line average. Hopefully that name makes more sense now that you've seen the details on how the parameter is computed. The RA parameter is calculated identically in both the ASME and ISO standard. However, the name of the parameter in the ISO standard is arithmetical mean height of the absolute values. Well, that name is obviously more descriptive. I find it much harder to remember than average roughness. The RA parameter is probably the most basic of all the surface roughness parameters. However, it is without a doubt the most commonly used parameter. In fact, right or wrong, the parameter is quite often the only parameter found on part drawings. This is not necessarily a good thing because the average roughness of a profile only tells part of the story. If you look at the profiles on this slide, you can see that they all have the same RA value, but the shapes of these profiles is quite different. In fact, they will behave quite differently when interacting with their environment. Comparing the RA value of surfaces machined using the same process is often quite useful. However, comparing the RA values of surfaces machined differently may not be so useful. In future webinars, we will discuss additional surface roughness parameters that will help us quantify the differences between these profiles. Okay, we are now going to have Abby do a demo of one of our GelSight systems. Thank you for listening. All
right, thank you, Pat. So before I share my screen and jump over to the GelSight software, I'm going to hold up a couple of the samples that we're going to scan. So the first one that we've got is this transparent plastic with a bunch of different textures on it that'll look pretty interesting to the probe. So we'll look at a couple of these. And then I have two examples of different powder-coated surfaces. So we can go in and compare the RA values on these curved surfaces here. So I've got our Series 2 system. And now let me jump over to share the software with you guys. All right, so the first thing that I'm going to do, in case some of you guys haven't seen the GelSight system, is press my fingertip into the top of the sensor so you can get an idea of the resolution. And now I'm going to go ahead and scan one of these patches on here. So I'm just going to press the probe into it and click the button one time to take the scan. The image acquisition's really quick, about 120 milliseconds. And the 3D data takes a little longer to generate on the tablet, but we've got some here already. And the first thing we like to do is look at the scan in 3D. So here's the 3D model of the patch we just scanned. And you could export this as an STL file if you wanted to. But for now, I'll just jump back over. And let's add a profile roughness measurement. So I just clicked profile roughness, and I'm going to draw a line perpendicular to the lay of the surface texture. And we can see what outputs we have. So in the advanced settings here on the right-hand side, I can pick my filter cutoff per my application. And I can see my average RA output and my RA output. I also see the profiles at the bottom of the screen. I can see my primary waviness and roughness profiles that Pat just described. We can also see on the profile, the primary profile takes up this whole blue line, but the waviness and roughness profiles start a little farther in, and that's because of that filter cutoff that Pat was just explaining. We can display just the roughness profile if that's what we wanted to take a look at. And then because we have an area scan system, we can actually increase the number of profiles we want to measure. So let's say we want to do 5 profiles evenly spaced within 1 millimeter. And I'll click Analyze here. So you can see that output, or the input line, just turned into 5 lines. And we're getting the average RA is the average of all 5 of those profiles. And the RA and the profile at the bottom refer to the center profile. And then we even have some quick reporting too. So I could just click PDF here. And there's the PDF report to go with my scan. Now let's jump back to capture and we can take a look at these other 2 samples that we have here. So for this first one, I'm just going to go ahead and take a scan of it. And once that's generated, we'll open it up and we'll measure the RA value. So here's the scan that we just took, and we can look at this one in 3D as well. And we can actually increase the scaling too. So maybe I want to see some smaller features on that surface texture. And you can see the curvature of that part. So we'll jump back over here and we'll add a profile roughness function again. And I'm just going to draw a line across my part. And we can see that output. And I'll turn on that primary profile again. So let's say I want to do the same exact analysis, but on another part so that it's as comparable as possible. So we can actually set our default analysis in the software. So I'll click Set Defaults here. And now every time I perform this analysis, it's going to have my input line in exactly the same location and my filter cutoff and profile count configured the same way too. So we'll jump back over to capture. And now we'll take a scan of this one. But I can actually run my analysis as a routine now. So I just selected profile roughness as my routine, and you can see that line show up in my field of view. So now when I take a scan, it's going to perform that profile roughness measurement and calculation along this profile line. So we'll press the probe onto my part and click the button. And it's going to generate my 3D data and perform that measurement now. So we'll see a green box pop up here. And that means my analysis is complete. So if we open that up, and there's our profile roughness result. So we can actually configure pass-fail criteria for this too. So if you wanted to configure it to have a red box for fail or green box for pass, you can configure all of that to run automatically as well. So with that, I think we'll start answering some of the questions in the Q&A. Sharing here.
Abby, I don't know if you can see the questions. I can read a few of them for us.
Yeah, let's read a couple of them.
Yeah, the first one is, can GelSight pick up a 1/1000th of an inch deep dimple on a mirror?
Yeah, so that's not going to be a problem for the GelSight system. We have, we talked about the pigment layer here, so we can look at it regardless of the optical properties. We're not going to have that problem with the reflectivity. And then the accuracy in the system for the Series 2 that I'm holding now is 1 micron plus 4% of the nominal, which in Imperial is 0.03 thou. So we'll definitely be able to pick that up even with the Series 2 system. And we do even have a Max system, which is our higher resolution system that goes down to 0.3 micron, or 0.3 micron plus 4% of the nominal.
Good answer. Yeah, the only question I would have is how wide is the dimple? And I'm in my head, I'm picturing a golf ball. So if it's similar to a golf ball dimple, it should be no problem. Next question is, every once in a while between scans, my resolution will go completely blurry. I have to either restart or reselect my gel. Then it is fine. Is there a way to fix this?
I'm assuming that you have a Series 2 system and it's an autofocus. Then you can basically just click on the screen to refocus the system. But if you want, you can connect with us offline. Just shoot us an email at support@gelsight.com and we can help you out.
Next question. This technology seems to be optimized for flat surfaces and surface roughness measurements. Is it suitable for damaged surfaces, characterization, and topography measurements for in-service components with complex geometries such as turbine blades? The interest in this case is to get all the dimensional and shape information of the damage that can be used for further risk analysis. A good case is turbine blades leading edges, for example.
Sure, yeah. So today, obviously, we're talking about surface roughness, but I would say turbine blade edge inspection is a big one of our applications. So inspecting defects along edges of blades, we can definitely do that. And curved parts, also not a problem. So if you want to talk a little bit more in detail about your application, we can connect too.
Okay, great. Next question. Is there any flexibility in the probing system? Can we make it like a roller for fast scanning of large areas?
Well, we don't have something like that now, I guess. So, maybe one day, right?
Next question. For larger surfaces, is the GelSight system capable of stitching the images? I can answer that.
Yeah, go ahead, Pat.
At the moment, we cannot, but let me just say, keep an eye out for something coming very soon. So. Does this quick RA measurement let us deal with complex surface corrections not flat or predictable curves like the polynomial corrections mentioned earlier? Or would we need to deal with that through a less quick pipeline? I would say yes, because like I said, the roughness filter itself basically will remove those long wavelengths. Quite often I see that if you don't do leveling or you don't do the polynomial curve to a curved surface, if you're only worried about roughness, those wavelengths end up getting filtered out anyhow. So the form fitting is not quite necessary, but it's in the software. There are certain scenarios where if your part is very out of level, you definitely want to level it before you do the filtering. But if we can measure it, we can analyze it for surface textures. Next question. Is there a calibration for every measurement if we change the location of the sensor and the surface type?
No, so you just need to calibrate each gel before it's used. So, and that doesn't mean every time I connect it to the probe. So let's say you have, 10 gels, you could calibrate all of them and then drop them in as replacements when you need them. But the calibration is independent of material. It's really just one set of settings for every material.
All right, 2 more questions. When will you have the essay webinar? Thank you. We are definitely going to cover the essay parameter in a future webinar. I don't have a hard date on that yet. So all I can say is keep an eye out. I'm sure we'll be putting on LinkedIn pretty soon. So, can the output data be transferred in a point cloud or CAD format?
Sure, so we can export the STL file of any of the scans that we just took. We do also output a TMD file, which is our raw 3D data. And a couple different software programs can open that, as well as we do have a repository on GitHub that'll help you write your own program to read that data too.
And the last question at the moment, how deep can imperfections be before the GelSight can no longer pick up the depth of it?
Sure, yeah, there's a short answer and a long answer to that. The short answer is about 1.5 millimeters. The long answer is it depends on the geometry of your surface, so as well as the depth of field of the camera and the thickness of the gel. So we've got about a 3 millimeter thick gel here, so the gel has to make contact to make a measurement, right? And then the aspect ratio of the surface of your part, if you could imagine, if you're looking at a really narrow crack that's really deep, the gel might not make it to the bottom of that. So we do typically look for that 1-to-1 aspect ratio to be able to reach the bottom of a feature.
Good answer. 2 more questions just came in. How is your system purchased? Is it the hardware and software in one go, or is there a subscription for the software and time limit?
Sure. So I think we'll follow up with you to answer that. But basically, the hardware is purchased, and we have a couple different software package options from Base, Core, Pro, depending which version you want. And they include upgrades for a certain amount of time, and then the maintenance would be purchased after that for future software upgrades beyond a year.
There's one last question. It's regarding a GelSight Mini. Do you want to take this one?
You can read it. We'll see. We might have to follow up. We'll find out.
All right. Can we use the GelSight Mini with the software you just showed, which is, I believe, no, right? Is that correct?
No.
And will the Mini be able to export point clouds or STL soon? We need the Mini for form factor reasons.
Yeah, so the Mini is a separate product. It's open source. You would be writing your own software for that. It won't work with our GelSight mobile software. But basically it uses the Open3D library. So whatever is in there, the open source Open3D library, you could access. But I don't know if we're planning to implement STL files in that at all. I think that would be something that we'd leave up to you in your software development.
All right, Abby, that's all the questions in the queue. We'll wait another 30 seconds to see if anybody has anything else to ask.
Yeah, sure. All right, well, I think we can pull up the last slide here to give kind of a
Mark.
sneak peek. Yeah, thanks, Mark. And this is just kind of a sneak peek into what's coming for the future webinars, some other topics. So we know we were asked about SA today, so that'll definitely be covered, and some more other of the R parameters.
Thanks, Abby.
All right. Thank you, Pat. And thank you guys for joining.